This is the first lecture from the Modern Chem text, looking at Chapter 8, Chemical Reactions. We're going to be, you might remember from earlier on this semester, or in the last semester actually, we talked about some of the ways you can tell that a chemical reaction has occurred. So there are some indicators that we can look for, including color change. So you can see down here, that's a nice example of some color change. We might have gas bubble formation. There might be a solid present when before there was not. Hopefully the term precipitate sounds familiar. And then oftentimes heat will be either produced in the reaction, which means you get, you can feel a warmer environmental temperature. And in some cases, heat will even be absorbed. So the products will feel cooler than what you began with, which is a really interesting process. So when we are representing chemical reactions or chemical equations, we have to remember that in order to show chemical change or in order to represent that a chemical has become something new, we have to break the associations or the bonds between compounds and rearrange their individual atoms. We do this by creating what's called an equation that is very much like the types of equations you would see in math. We always start with the reactants on the left, so we read left to right, and we begin with whatever compounds or elements we have at the start of our experiment. And then we show what is produced or created by using an arrow. This arrow represents a term called yield. So the reactants yield the products. We're not creating something new. We're just rearranging something old so that it produces a new version, perhaps. We have to remember that always the law of conservation of mass has to be accommodated or has to remain valid. So any atoms that are present in the reactants must also be somewhere in the products. They just might be rearranged or in a new form. There are two basic equations that we will use. There are word equations, and I bet you can predict what those involve. So word equations are something like hydrogen plus oxygen yield water. So when we read an equation out loud, we never say hydrogen plus oxygen makes water. We always say yields. We don't say equals because they don't equal water. They're two totally different things, but they do have some of the same components. The drawback or the limitation of word equations is that it doesn't usually tell us the ratios of the components. It's sort of like saying, sure, you can make chocolate chip cookies, you just need sugar and milk and eggs and flour and vanilla and chocolate chips, and then you'll have cookies. Well, that doesn't do you a lot of good if you actually want to make the cookies because you don't know how many of each thing to use. A formula equation is much more detailed. It generally involves chemical formulas rather than the words or the full names. So for our same equation here, hydrogen, which is in the form of H2 gas, plus oxygen, also in the form of a gas, yields water. So it shows us the form that the hydrogen and oxygen are in, and it shows us the formula for the newly created compound. There will often be a coefficient or a large number in front of the formula itself that represents how many numbers of moles are needed for this reaction to occur or how many numbers of moles are produced through the course of the reaction itself. And I'll show you an example of that here on the next slide. So sticking with our water example here, when we analyze chemical equations, we have to be sure that we accurately represent all of the atoms that are necessary for a reaction to occur. So the number of individual atoms on the left or the reactant side of the equation must be equal to the number of atoms on the right, or the product side. This is not always the case when you just write the formulas involved in a reaction, just like with a recipe. Just saying flour and sugar and eggs doesn't represent how many of each thing you need, what the units would be. So we do that by showing that some parts of the equation or some parts of the reaction have more than one unit. So when we count here, let's start with looking at our hydrogens. We have 2, that should be a subscript. Let me put it here again. We have 2 hydrogens on the left, in the way that our reaction is currently written, and we have 2 oxygen atoms on the left. And then we show those yielding a product that contains 2 hydrogen atoms and 1 oxygen. So there's something wrong here. We are showing that 1 oxygen has been lost to the environment, which we know isn't true. The oxygen doesn't just disappear when water is made. So we have to represent how many units of each part of this equation would actually exist were this to happen in real life. And what that means is for every unit of oxygen, right, every individual oxygen, we need twice as much hydrogen in order to create this product. Water is always 2 times as much hydrogen as it is oxygen. So in order for that to happen, what we would have to have in our recipe is we would have to start with twice as much hydrogen as we have oxygen. So we represent that by saying we need 2 moles of hydrogen for every 1 mole of oxygen gas, and that will produce a grand total of 2 moles of water. Right? So if we think of these as individual atoms, there's H and an H, an H2 and an H2. They look exactly the same. And then we have an oxygen bonded to an oxygen. When those compounds rearrange to make water, what we're going to end up with is 2 of the hydrogens will partner up with 1 oxygen, and then the other 2 hydrogens will partner up with the other oxygen. And so we can check. We have 4 here? Yes. And we have 4 hydrogens here. We have 2 oxygens here, and then 2 oxygens there. So all of the atoms that we began the day with, we have finished the day with, and we have the compounds are exactly the same as our original formula. We still have hydrogen gas and oxygen gas making water. We're just showing what the ratios would have to be in order for this reaction to take place. A lot of times we will also provide some information within the equation itself or the chemical formula that tells us about the materials that we're dealing with. So in that last equation, right, we had 2 moles of hydrogen, and I told you it was a gas. So you'll often see parentheses with a G to represent this is a gas. And then we have our oxygen, also a gas. And this goes on to create 2 moles of water. So if I were doing this in my home laboratory, and I've got my hydrogen gas and I've got my oxygen gas, and I put them together, wouldn't you want to know what to expect coming out, right? A lot of times if you bake or you cook, with a recipe there will be a picture, so you have some idea of what it's going to look like when you're done. Otherwise it's kind of a shot in the dark as to whether you've done it right. It's the same thing in chemistry. We like to have some idea of what we're starting with and what we should expect to end with. So often you will have your products as well. In this case, oxygen gas and hydrogen gas, when they come together, they actually make liquid water, and we represent that by L. Sometimes we will have solutions of product. So some reactions only take place in water or take place more easily in water, and the water is just an environment or a vessel for the reaction to occur. It's not actually involved in the reaction at all, right? So it's like your stove. Your stove is the vessel for making chocolate chip cookies. It It's not part of the cookies themselves. So in those cases, when there's a water environment that's helping this reaction occur, then we write aqueous to just represent the reaction is happening in water. Some other symbols that you are likely to see, so I don't know why this thing keeps ditching my arrow. There's my arrow to represent yields. Sometimes reactions can go both ways. We can create something new, but if we leave that something new sitting around long enough, a lot of times it'll start to go back to its original state, which is really interesting. Think of it sort of like an ice cube, right? You can freeze liquid water to make an ice cube, and then when you take the ice cube out of the freezer, if you let it sit there long enough, it will reverse itself back to a liquid. And we represent that by showing an arrow that moves in both directions. So this reaction can go in both ways. We will occasionally also say, in order to make this happen, you need heat. So like our cookies, for instance, you could mix eggs and flour and sugar and chocolate chips and let it sit for days, months, years, and it will never make chocolate chip cookies without the addition of heat. So you could put all your ingredients over here, show that with the addition of heat, then you get delicious and wonderful chocolate chip cookies. There are other reactions that require the addition of heat as well. Sometimes we might put a catalyst, which is a compound that helps the reaction along, maybe water, for example, but isn't involved in the reaction itself. And very occasionally in chemistry, you'll see some kind of a pressure reading, let's say, I don't know, 1 atmosphere, that just says in order for this reaction to occur, there's a special air pressure that's required. We don't deal with that a lot, but I just wanted to mention it. The last thing is just a review of the rules for chemical equations, and we generally refer to this as balancing. We need to make sure that the equation represents accurately what happens in this reaction, and it shows the proportions that are necessary to get the reaction to take place. So the first thing is to identify both the reactants and the products. Make sure you have your formulas written correctly. That's going to be a huge deal. If your formulas are slightly off, then your numbers of atoms will be slightly off. Remember that if you are given a word equation, you might not know the exact formula. It might say water and iron sulfate react to form blah, 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 blah. So then you have to go back and look at the charge of the iron, the charge of the sulfate, and make sure that your formula balances out to a neutral charge of 0. If you're given the formula, then just make sure you copy the formula correctly when writing the equation. Then you count the number of atoms on the left and the number of atoms on the right. I like to make a list. So if I'm dealing with, we'll say iron sulfate and water, I make a list, iron sulfate, looks like this. Water has H and O. And then I just count how many are on the left and how many are on the right. And then I can adjust as I need to. And we'll do lots of these in class for practice. Then you add coefficients as necessary to balance. If they're already balanced, then don't add any coefficients. The most important rule of balancing equations, and you'll hear me say this a million times, is you can never, ever, 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 ever change the subscript to try and balance out. Changing the subscript makes a new compound. You cannot create a new compound. You have to work with the compounds you're given and balance the ratios. You cannot change the compounds. That changes the whole reaction. In order to easily, or more easily, I guess I should say, balance the equations, there are a couple of kind of suggestions I would make to you. So balance anything that start with anything that only appears once. So in some cases you'll have compound or reactions where there's water and there's oxygen gas and there's something else. So you have oxygen in multiple compounds here. Choose an element for starting out that has that's only in one compound on each side. That will make it easier for you. As much as possible, keep polyatomic ions together, so like sulfate in the earlier example. If sulfate is on the left and it's on the right, then keep it together. Don't break it up into sulfur and oxygen. And then wrap up with the most common elements, the ones that are usually present in most reactions and can be present in a variety of forms. So end with hydrogen and oxygen. That should help make the process a little bit easier. We'll do some of these in class when I see you next. So please bring in a couple of questions for discussion, 3 questions, and write your summaries, and I'll see you soon.